As expected, at regular intervals in recent years, a sign has pierced the quiet of the room and arrived on Earth. It's not a satellite or any man-made object. It's a sign from profound space, which is a mystery researchers call GPM J1839-1842. This sign, caught by one of Earth's most remarkable telescopes, has turned into the subject of worldwide interest and debate. Where might it be coming from? And why should we care? Today, we'll dive into an infinite criminal investigator story that challenges how we might interpret the universe itself. Let's get started. So how might we check out and open the secrets of such a sign? The instrument that makes our space investigation possible is radiocosmology. The story starts in the 1930s when American physicist Carl Jansky was investigating radio impedance. What he found was startling: radio waves radiating from the Milky Way. This accidental discovery marked the beginning of radiocosmology. Unlike traditional stargazing, which depends on visible light, radio astronomy pays attention to the universe. It tunes to frequencies blocked off to the natural eye, revealing heavenly phenomena that would otherwise stay hidden. Since its commencement, radio astronomy has undergone an innovative revolution. Today, radio telescopes are wonders of engineering, capable of receiving signals from impossible distances. In the remote outback of Western Australia sits a space investigator unlike any other, the Murchison Wide Field Array. It's not just a telescope, it's a complex network designed to investigate the farthest reaches of the universe. Made up of thousands of receiving antennas scattered across a barren landscape, the Murchison Wide Field Array is an engineering achievement and a testament to human curiosity. Each antenna is like a finely tuned ear, listening eagerly to a murmur in the background. A team of dedicated scientists and engineers work tirelessly to align and maintain this intricate system. Their goal is to capture signals across a wide range of frequencies. This is significant for studying different heavenly phenomena, as each one emits its unique radio signature. When captured, these signals are processed in a state-of-the-art data center, where powerful algorithms sift through the cosmic noise to identify patterns and anomalies, turning raw data into meaningful scientific revelations. Fascinating yet quick radio explodes, or on the other hand, FRBs, fast radio bursts. These high-energy peculiarities are unquestionably short-lived, lasting only milliseconds, yet radiating as much energy as the sun produces in nearly a century. It was in this astronomical chaos that our puzzling GPM J1839-10 signal was found. Dissimilar to other signals, this one has a musical pattern and has been appearing at Earth at regular intervals for the past 35 years. What separates this signal is its consistency and longevity. While most celestial signs are random or short-lived, this one has proven to be both stable and steady, making it a subject of great study and debate. Not bad, but not great either. Unlike time signals that travel every which way, GPM J1839-10, or an obstruction of some sort, thorough checks were made, but the signal persisted. Subsequent observations only confirmed its presence, making it one of the most enduring mysteries of radio astronomy. So, what makes GPM J1839-10 unique? Its 22-minute periodicity resembles a metronome in a vast ensemble of cosmic signals, a rhythmic constant in an ocean of variables. Further investigation reveals even more peculiarities. The waveform doesn't follow the usual profiles of known celestial radio emissions. Its frequency and amplitude have details that have yet to be fully understood, complicating an already baffling mystery. Numerous theories have been proposed, from rotating neutron stars to highly magnetic magnetars, as well as even more exotic hypotheses like the connection between binary black holes. However, none of them perfectly meet all the criteria, leaving the scientific community in a state of intrigued bewilderment. When it comes to mysterious radio transmissions from space, suspicion often falls on pulsars. These celestial beacons are known to emit light beams and waves, making them prime candidates for any unexplained cosmic signals. But what are pulsars? Pulsars are neutron stars born from the remnants of massive stars that have gone supernova. They rotate at incredibly high speeds, and as they spin, their magnetic fields generate beams of electromagnetic radiation, including radio waves. These waves travel through space like the light beams of a lighthouse. When these beams cross Earth, our radio telescopes detect them as regular pulses, hence the name pulsars. The signals from pulsars are generally very regular, often with millisecond precision. This consistency has even led to some pulsars being used as space-timekeepers to help with tasks like spacecraft navigation. So, could GPM J1839-10 be a pulsar? At first glance, one might think so, given its rhythmic 22-minute period. However, if you dig deeper, the differences become clear. Unlike typical pulsar signals, which have a constant shape and amplitude, GPM J1839-10 exhibits characteristics that set it apart. Its waveform doesn't follow the patterns we usually associate with pulsars, and its amplitude displays variations that remain unexplained. Furthermore, the longevity and consistency of the signal contradict what we know about pulsars. These cosmic objects can slow down over time due to a loss of rotational energy, which would affect the timing of the signals they emit. However, GPM J1839-10 has remained unchanged for over 35 years. To summarize, although pulsars are often the prime suspects behind mysterious radio transmissions, this time they seem to have been ruled out. While pulsars are frequently the first candidates for unexplained cosmic signals, magnetars make an appearance on that list as well. Magnetars are neutron stars that don't quite fit the pulsar model, with incredibly powerful magnetic fields that challenge our understanding. To grasp the magnitude of a magnetar's magnetic field, consider this. It is about 2 quadrillion times stronger than Earth's magnetic field and 20 trillion times stronger than a refrigerator magnet. These are magnetic fields of immense power. Most of the way to the Sun, magnetars are known for their odd properties. They transmit X-beams and gamma beams. However, they can likewise deliver radio outflows. These discharges are frequently related to heavenly quakes, seismic occasions on the outer layer of a magnetar that release tremendous sums of energy. Imagine a tremor, but on a gigantic scale. These heavenly seismic tremors can distort the attractive field of the magnetar, causing the release of energy as electromagnetic radiation, including radio waves. So, could a magnetar be the source of our puzzling GPM J1839-1842 signal? Well, from the start, it may seem possible. After all, magnetars are known for their abnormal behavior. However, the nature of starburst fails to explain the consistent 22-minute signal duration and its longevity. Starbursts are inconsistent events, and their discharges won't have the musical, clock-like accuracy of GPM J1839-1842. While they offer an interesting possibility, the evidence, or lack thereof, brings us back to the drawing board in search of a better explanation. As we continue to explore astronomical theories regarding GPM J1839-1842, white dwarfs are another consideration. These remnants of stars that have depleted their atomic fuel are extraordinarily dense and have strong magnetic fields, which could hypothetically cause radio emissions. Might a white dwarf be the signal producer behind GPM J1839-1842? While their magnetic fields are strong, they don't exactly match the features seen in GPM J1839-1842. Another frontier theory leads us to the unique interactions between stars and exoplanets orbiting them. In this astronomical dance, the magnetic fields of the star and exoplanets can connect in ways that could indeed create unique radio emissions. While this theory offers an interesting avenue of investigation, it also comes with its own challenges. Such interactions would likely produce a wide range of signals, rather than the steady 22-minute cycle observed with GPM J1839-1842, potentially producing radio waves again. While this theory breaks new ground, it's not entirely consistent with the data we have. Magnetic interactions between binary brown dwarfs are likely to generate a more turbulent signal, rather than the rhythmic, clock-like beat of GPM J1839-1842. Another perspective is emerging that takes into account the environment in which the signal exists. Could surrounding astronomical debris and solar winds impact the signal patterns we observe? Imagine a radio transmission traveling through space and encountering space rocks, gas clouds, and surges of charged particles along the way. These environmental elements can act as space filters, altering the characteristics of the signal by the time it reaches Earth. This idea isn't purely speculative. Studies have demonstrated that space debris can indeed influence the properties of radio signals, causing changes in amplitude and even frequency. But is this the case with GPM J1839-1842? Does it fluctuate in ways that could explain some of its features? Interestingly, the results of the fast radio burst 20180916b offer some parallels. This particular FRB showed patterns that were initially perplexing but were later found to be influenced by nearby conditions, including the presence of a nearby magnetar and the surrounding large plasma. Could a similar environmental impact affect GPM J1839-1842? Although the settings are different, the possibility that local space conditions can influence radio transmissions adds another layer of complexity to our understanding. As we approach the final frontiers of this study, it's time to consider the broader implications of this mysterious signal and what the future holds for its study. Fortunately, the source of GPM J1839-1842 remains a subject of ongoing investigation. Researchers are continuing their observations and examining historical data, looking for similar phenomena in the Milky Way. Their ongoing efforts are aimed at solving this mystery, and their early results are promising. The discovery of GPM J1839-1842 has confirmed that ultra-long period radio sources are not as rare as once thought. This suggests that upcoming studies in the cosmic plane may uncover even more examples, expanding our understanding of these confounding signals.